Welcome back, everyone. This is Professor Herring. In this video, we're going to learn how to draw Lewis structures. We're also going to talk about and learn about formal charges and how we can use them to determine which Lewis structure is best. So a Lewis structure is one way to represent a molecule. And if you take a look at the molecular formula, the Lewis structure tells us how things are bound together. And I'm going to present you with some rules that indicate for you how to draw the Lewis structure. The first step is to count out the number of valence electrons. So let's say that you have water. You have 2 hydrogens and 1 oxygen. And each hydrogen provides 1 electron, each oxygen is 6. If you have a negative charge, you're going to add an electron. So in the case of the hydroxide ion, you have 1 from a hydrogen, 6 from oxygen, and 1 for the extra negative charge. If you have a positive charge, then you're going to subtract an electron. And so if we have hydronium ion that has 3 hydrogens for 3 electrons, 1 oxygen for 6, that gives you 9. And then you take 1 electron away due to the positive charge. Hopefully the effect of those charges makes sense. If a substance has a negative charge, then it has to have had an extra electron. And if it has a positive charge, then it's deficient electrons. So you're pulling 1 away. After you've counted up the number of valence electrons, what you want to do is write out the atomic symbols and connect those atoms with single bonds. Many students start out by writing out with things with multiple bonds, and it just doesn't make sense to do it that way. You're going to make a lot more problems. So you always want to write out only with single bonds first. The first thing you do is that you make sure that the central atom is the least electronegative element. The only exception to that is hydrogen. Hydrogen can only form 1 bond, and so it's never going to go in the center of a molecule. Oftentimes, a symmetrical formula will mean that there's a symmetric structure. And then finally, for oxy acids, those are acids that have oxygen in them, you're going to connect oxygen to the central atom, and usually a hydrogen is connected to that oxygen. So an example of that is sulfuric acid. The least electronegative element, not including hydrogen, is sulfur. It goes in the middle. The oxygens are connected to that, and then the hydrogens are connected to the oxygens. The third rule is to distribute electrons, first as lone pairs to complete the octets of atoms. And if you don't have enough electrons, only then do you start making multiple bonds. If instead of not having enough electrons, if you had too many, then you put the extra electrons on your central atom. So let's do an example of this with nitrosyl chloride. First step is to count out the valence electrons. You have 5 valence electrons from nitrogen, 6 from oxygen, 7 from chlorine. That gives you a total of 18 valence electrons. Then you want to write out the atomic symbols, putting the least electronegative element in the center. So nitrogen is less electronegative than the other 2. You'll put that in the center. And the other 2 go on the exterior. And connect them with single bonds. So this right now uses up a total of 4 electrons. Remember, each single bond is 2 electrons. Third step is to complete the octets with the lone pairs. So if we've used 4 electrons, then that means there's 14 electrons remaining. And if we put that around the chlorine, that's 6 electrons. Nitrogen, that's 10 electrons. Oxygen, that's 4 electrons. That's a total of 14. But that's not going to work. Oxygen does not have a complete octet. So it's in this case that we now need to form a multiple bond, a double bond. So how do you decide where the double bond goes? Well, you're going to need to form the double bond with the element that is deficient. Since oxygen is deficient in the electrons, it needs to form that double bond. And the electrons are going to be the electrons that came from the nitrogen. In other words, these electrons here are going to go and form a double bond there. That leaves us with this molecule. Now everyone is satisfied. And notice the absence of the fifth step. We've used all 18 valence electrons, there's none left over, and therefore we've completed the Lewis structure. I'd like you to try this next one. Pause the video, read over the question, and try and solve it on your own. Note that when we talk about bonding pairs, this is referring to a bond, and a non-bonding pair refers to a lone pair of electrons. Welcome back. So what you should have done for this one is seen that we have 4 valence electrons from carbon and 28 total from the fluorines. There's 4 fluorines and each one has 7, giving us a total of 32 valence electrons. Put this carbon in the central spot because it's the least electronegative element. There's also only one of it. And then the fluorines on the exterior. Distribute the electrons until they're either all satisfied or you run out. If you have extras, then those go on the central atom. If you count up the electrons, we have 32 represented, and that gives us a total of 4 in bonds and 12 non-bonding pairs. All right, try one more. Pause the video and try this one on your own. Welcome back. So this question is asking about the types of bonding and the lone pairs within the Lewis structure. You're given a hint that each nitrogen is connected to 1 hydrogen. First, we want to count up the valence electrons. The hydrogens, there's 2 of them, and they each have 1 valence electron. There's 2 nitrogens, each with 5 valence electrons, giving us a total of 12. When we put the nitrogens in the middle and the hydrogens on the outside, draw single bonds in between them first, and distribute the electrons. When we do this, we notice that there's not enough electrons, and so we need to draw a double bond replacing that lone pair of electrons. At this point, it's satisfied, and the question asks, what type of bonding do we have? Well, we don't have a triple bond. We don't have a single bond. Each nitrogen does have 1 lone pair. Hydrogens are never going to get lone pairs of electrons. And the nitrogens only have 1, so they can't have 2. All right. We're going to now talk about, I'm going to show you another example. So if we're asking which is the best Lewis structure of phosgene, it turns out that you could draw multiple Lewis structures to represent a given molecule. And so what we want to do first is count up the valence electrons, make sure that what we've represented is correct. This one, A, is not correct, and that's because it has 26 valence electrons. If you look and count, you can see that we have too many electrons represented. Therefore, A does not represent phosgene. If it did represent anything, it would be COCl2 with a 2- charge. So between B and C, how do we determine which is the best structure? The way that we answer this is by using what are called formal charges. A formal charge is really just a formalism. It doesn't actually exist, but it compares the number of electrons that an atom in a molecule possesses to the number of electrons in the free neutral atom. So it's simply a bookkeeping method that tells us where the charges would be if there were charges. If an element has more valence electrons than the neutral atom, then it bears a negative formal charge. If it has fewer, then it has a positive formal charge. Shown here is an example of calculating the formal charge carried by an oxygen atom. I'm going to walk you through that process. So we're saying if we have hydroxide and we wanted to calculate the formal charge on oxygen, here's what we would do. Draw out the oxygen element and count up its number of valence electrons. Then when it's within the bond, within the molecule, you're going to account for both the lone pair electrons, but also the electrons that are within the bonds. And because this is a covalent bond, the electrons are shared. And so oxygen gets to keep, quote unquote, one of the two electrons. And so what we see here is that it had 6 valence electrons, but now it has 7 within the molecule. And by using this calculation, we can see that the formal charge is a -1. Now, another way to do this, which I prefer, is a little different from what's shown here and what's shown in the ebook. And it's simply to compare valence electrons to how many it has when it's bonded. And it's very similar, but the difference is that I'm not actually subtracting. I'm just more thinking intuitively. So we know that we had 6 valence electrons, and then it now has 7 electrons. So if we were to describe this in words, we could say that the oxygen gained 1 electron. Well, each electron is negatively charged, and so if it gained an electron, that means it gained a negative charge. And since it gained 1 electron, it has a -1 charge. And so I prefer thinking of it that way, simply as a process of comparing how many it had to how many it now has, and seeing if there's a net increase or decrease of electrons. So let's go through a problem here and calculate the formal charges for the 2 remaining structures to see if we can determine which one is best. Chlorine has 7 valence electrons in the free neutral atom. And the purple chlorine has 6 lone pair electrons, represented here. And it has 1 bond, and so therefore it gets 1 electron from those bonds. So it has a formal charge of 0. The chlorine that is yellow has 7 in its valence. It only has 2 sets of lone pairs, and so a total of 4 lone pair electrons, but it forms 2 bonds. And so it gets half of those electrons for a total of 2, which means it has a formal charge of +1. The purple oxygen has 6 normally in its valence. It has 4 in lone pairs. It has 2 bonds, and therefore 2 electrons, and so it has a 0 formal charge. Finally, the oxygen that is orange, 6 normal electrons in its valence. It has 6 in its lone pairs, and then 1 from the bonds, which gives it a formal charge of -1. So the question of which structure is better comes down to determining the formal charge. In order to have the best Lewis structure, we want to minimize the formal charges. And so that means that the Lewis structure on the left is going to be best. We want to have the small minimized formal charges. We want them to be as close to 0 as possible. And keeping in mind that essentially you can think of it as the absolute value. So in other words, a -2 is worse than -1. And that's because it's farther away from 0. We also want to put the negative formal charges on the more electronegative elements, and the positive formal charges would go on the less electronegative elements. So applying the first rule, that we minimize formal charges, that means that structure B is better. Something to note here is that the sum of the formal charges is the net charge on the ion, and so you can use that to check your structure. Since phosgene had no net charge, the sum of the formal charges should add up to 0. On the left, we have 0, 0, 0, and 0, and those add up to be 0. And here we have 0, 0, +1 and -1, and those add up to be 0 as well. So they're both adequate structures, but the one on the left is better. So another word about formal charges here. Again, they are not actual charges. They're just a formalism. We'll learn later about oxidation number, and if we were to look at the same structure, hydrogen chloride, using the oxidation numbers, hydrogen would have a +1 oxidation number, chloride would have a -1 oxidation number. But if you look at the formal charge, both of those would have a value of 0. But in reality, what we see is that they have partial charges. And when we talked about bond polarity, we talked about how the elements don't share their bonds equally. And because of this, what we really see is that there's a slight partially negative charge on chlorine and a slight partially positive charge on hydrogen. And so the formal charge doesn't actually account for the differences in electronegativity. The partial charges are the real measure of a charge. Let's give you a couple opportunities to practice here. Pause the video and read over the prompt to see if you can solve this on your own. Welcome back. So to solve this question, what we first need to do is draw out the Lewis structure. We need to count up the number of valence electrons, which is 24. Put nitrogen in the middle of the oxygens and draw single bonds between it and the oxygens. Then we distribute the lone pairs of electrons. What we notice here, though, is that the nitrogen is not satisfied, and so we need to form a double bond between it and one of the oxygens. After we do this, we're now prepared to evaluate the formal charges because we're following the octet rule. The oxygens with the single bond are going to have a formal charge of -1. Oxygen in the double bond is going to have a formal charge of 0. And nitrogen with a formal charge, nitrogen with 4 bonds is going to have a formal charge of +1. So that gives us a total formal charge of -1, which is what we should get. We can indicate the overall charge using these brackets. And that would indicate that the whole molecule has a negative charge on it. And we indeed see that if you sum up the charges, you get a -1 charge. And so the nitrogen atom ends up with a +1 formal charge. In reality, it's going to be somewhere between 0 and 1, but the formal charge is that it's +1. Remember when we talked about the rules of valence earlier and how the rules of valence dictate the number of bonds that an element wants to form? Notice that the elements that are forming bonds equal to their valence are ending up with formal charges of 0. This is a very important pattern that we will utilize to our advantage. In this last question of this video, we're asking you to think about which Lewis structure is best. Remember, to answer this, you need to think about the formal charges. So go ahead and evaluate that in this case. Pause the video and try this out on your own before coming back. Welcome back. So the first thing you should do is count up the electrons. If you paid close enough attention, you would see that not all of these structures are even possible based on the structure. Carbon contributes 4 valence electrons, oxygen contributes 6 for a total of 10. Well, how many does structure A have? It has 2, 4, 6, 8, 10, 12, 14. That's not carbon monoxide. Structure B has 2, 4, 6, 8, 10. So this is possible. Two, 4, 6, 8, 10, 12. That's not possible. 2, 4, 6, 8, 10 electrons. So that's possible as well. What you want to do at this point then is determine the formal charge. Draw the Lewis structure, single bond in the middle. We get to this point. We can see that we're not satisfied here. The oxygen needs more bonds, and so this structure shows us satisfying the octet rule. And that's the difference between this one, which is actually very similar to structure B, and this one, which is structure C. When we look at the formal charges, we can see that the formal charge on carbon atom is -1, and the formal charge on oxygen would be a +1. And while this is not very good, these are the formal charges on the carbon monoxide atom. And we'll talk about a little bit later about the implications of what this might mean in terms of the stability of the molecule. So, and just to keep in mind that this is just an accounting tool. It does not describe the actual charges on the elements. They would have however, potentially a partial charge. Actually going in that direction. That's it for this video. Thanks for watching, everyone. If you have questions, ask on Piazza, in office hours, or in recitation. Have a good day.